In this video, we'll move into section 6.4, where we'll start to actually describe and use the derivatives of the log functions. Now, I know the section is entitled Derivatives of Log Functions, but we're now at the point, as soon as we learn a new derivative, we move right into dealing with the antiderivative and using that as well. So, once again, a lot more work, and now you'll already start to see how we need some of those pieces from 6.3. This is where most of your actual test material comes from. Some of the limit stuff we did is certainly going to be a part of the test. But again, most of what this upcoming test is going to focus on is the calculus of these new functions. So derivatives, limits, antiderivatives, and the problems that use those concepts. So right off the bat, we are going to start off focusing on the natural log x function. So we are going to make a derivative rule and add that to our chart. Now, there's several ways I can do this, but what I'm going to do, ultimately you need to just know the derivative and be able to use it, but I'd like to demonstrate where that derivative comes from. And this is actually a very clever little technique that we're also going to use for the inverse trig functions when we think of their derivative. So just looking at this situation, and I ultimately want the derivative, so I'm going to use the Leibniz notation. Instead of just y prime, I want dy dx. But the issue is I don't know anything about natural log. So I'm going to apply the inverse idea. If y equals natural log of x, then e to the y power equals x. Using that inverse, natural log is base e to this power equals x. Or e to what power gives me this, and the y would be over here. Either way pushes me over to here. Now, I want dy dx. So I'm going to take the derivative, but now I'm not in my nice function setup. Instead of having f of x equals, so I could just immediately move from f into f prime for notation, now I need to use implicit derivatives. So if I want dy dx, I have to take the derivative with respect to x. So I'm going to jump to the right side. The derivative of x is 1, and with respect to x, I know some people tell you to mark it dx over dx, but even as notation, you could just cancel that out. But on this side, so this side is just a nice clean 1. The derivative of x with respect to x is a nice clean 1, but over here, the derivative of e to the y is itself, but now I need to mark that I took the derivative of y with respect to x, so this gets marked dy over dx. And now that's the little issue with implicit derivatives. Hopefully you remember that from Calc 1. We're not going to do that too much here, but a quick reminder that the issue when you use implicit differentiation is that now you have to solve this for dy dx when you're done. So I'll just divide the e to the other side, so I get 1 over e to the y. But there still is a little issue here. The issue that's coming up here is that this is supposed to be the derivative of this function. But remember, right, Calc 1, this function is in terms of x. We want the derivative in terms of x as well. Right now we've got the derivative in terms of y, but now we're going to take advantage of just a clever little observation. Look back here. We started with this as the original function, and then we are able to manipulate this into this, either using the definition of the inverse or just manipulating raise both sides, base e. On this side, the e and the log would cancel, you just get x, and here's your e to the y. But now on this line, notice, I've got an e to the y, but I know in this line that e to the y is the same thing as x. So this derivative becomes 1 over x. And now, let's jump right over here to the chart. So now our simplified version, the derivative of natural log of x, is just 1 over x. So even if you're a little confused by how I did this work over here, ultimately this is what you are responsible for. Now that rule has been established, so now we can use it. And as we keep seeing over and over again, this is the basic rule, but we really need to be ready for chain rule. So if this was more than just a log x, log of x cubed, log of cosine, log of 4x squared minus 6x, if it's anything more than that, we treat this internal part like a u, and that would be chain rule. The derivative of the outside, the log, would give me a 1 over u instead of a 1 over x. And that u, whatever it is here, is exactly copied in the denominator here. And then we will finish by multiplying by the derivative of u. So, this will probably be in the second part of this video. I really want to take a lot of time doing the derivatives, and then we'll start talking about how to use this as anti-derivatives. We've already got our u notation. There's a little extra catch when you go backwards from here to here, but we'll come back to that in a few minutes. That, again, is our basic new rule. So let's jump right in. Let's find derivatives. Find the derivative for the following functions. So we're going to use this rule a lot. Let's start off with a nice one. If I function a of x is equal to 4 log x minus 3 log of 5x plus log of x to the 4th. I'm just working on some very basic pieces so far. So any derivative, we take a quick moment, see how everything is attached, see how everything is connected. Nothing too fancy in this one. Everything is looking good, right? 3 separate pieces. That's not multiplication. That's not multiplication. These are just inner outer, but nothing too crazy. They're still somewhat basic. So you could literally just use this first one and use this rule, but then for the others, just start to embrace the chain rule. That u is 5x here, and you get an extra derivative of 5x at the end. U would be x to the 4th here. You get an extra derivative here at the end. So that's where we're going. And now we could just one at a time take those derivatives. 4 times 1 over x. The multiplier just pushes along. The next one, the minus 3 pushes along. But now again, you've got a little bit more here. So the derivative of log of 5x. Oh, by the way, you will notice everything here is natural log. And especially for math people, natural log is kind of the only log we use. So we eventually get to a point, as you notice I'm already doing, instead of always calling it natural log, we start just saying log. And it's already understood that we're talking about natural log. So, yep, log of 5x, there's a u. So taking the derivative of the log, this goes into the denominator. I get 1 over 5x. But the fact that there was a little bit more here, I still need the extra du part at the end. What is the derivative of 5x? It would be an extra times 5. Plus, this last one, another log of u. I would get 1 over u times the derivative of u. So once you get the hang of it, log is actually pretty nice. But here's a couple little things that definitely throw people off in the first place when they first get started. Number one is that in your original function, I've got a bunch of logs, but in the derivative, the log is gone, right? When you look at this rule, this isn't 1 over log of u. That's a very common mistake. People after the e section, they're used to repeating whatever e to the u is in the original function. The derivative is that exact same e to the u. Then you do the derivative u. And I think that might be a part of it. But for some reason, some people, when they first get started, they start doing 1 over log x, 1 over log 5x, 1 over log x to the 4th. That's not what the rule is telling us. The log is gone as you take the derivative. And the second issue, the u is the same, but it's changed positions. Here, it was just a plain x. Now it's 1 over x. A plain 5x, that 5x is in the denominator. A plain x to the 4th, that x to the 4th is in the denominator. So just those little things to make sure you're getting on the right track. As far as cleanup is concerned, again, this is a good answer, but notice there's a lot of little things we can do to make this a little nicer. 4 times 1 over x. The book would definitely clean that up to 4 over x. Here, I mean, there's a lot of little things here. You could start talking about, well, 3 over 1 times 1 over 5x times 5 over 1. But to notice, the 5s would cancel. So this would simplify to just minus 3 over x. And over here, plus, we would end up having 4 times 1. We still have a 4, but the x cubed over x to the 4th, we could simplify that. I mean, and now you could keep going. Now all of a sudden we've got some like terms, and this could be combined. They already have a common denominator to 8 over x. By the way, this actually, all of them have the common denominator. 4 minus 3 plus 4, we would end up with 5 over x. So little things, right? This is a spot, this was a good spot for your answer, but all the little things that can be cleaned up. And 2 more little things before we move on to the next one. I mentioned in the previous video, we're going to take advantage of the expansion properties of logarithms. Technically, this could be expanded. This could be minus 3 times log 5 minus 3 times log x. Right? The minus 3 is out in front, and that multiplication would become log 5 plus log x, and then I distributed the minus 3. So just notice, if we did that first, this derivative is 0. There's no variable. It's just like saying, what's the derivative of minus 3 by itself? The derivative would be 0. Include the log 5, that doesn't change anything. That's all just a number. That derivative would be 0. And then the minus 3 log x, we could kind of jump to this a little bit faster when we take the derivative. Similarly here, this, we've got x to the 4th power. That could become 4 times log x. And look, that's actually exactly what we had here right off the bat. So that could have been manipulated, and not like this was hard, but just that would be a little bit easier. But notice, again, this first problem, nothing was that complicated, so there was nothing wrong with kind of just jumping in. But now as we move to problem number 2, still going to keep it a little easy before we start seeing the full expansion. Why that is so helpful and how that can make our derivatives a lot easier. But again, let's take our time. Number 2, let's look at b of x is 2 times the log of x to the 5th minus 6x plus 1 minus 2 log of cosine x. And you know what, let's just make this a minus 12, just so it's a different number. And that's good enough for this problem. Still, good habits. Directions are fine, the derivative. What's our situation? I can't say it enough, everybody. We can't see that as multiplication. This is not product rule. Again, it's just like sine of x to the 5th minus 6x plus 1. Just like the trig functions. There needs to be something on the inside of a log function. So this is not multiplication. This is inner outer. This is chain rule, and that's exactly why I have this set up the way I do, to get us ready for chain rule. Honestly, and now we've only done, this is only our second problem, but a lot of people, they completely scrap this. It's so rare that you get exactly a log x that a lot of people don't even bother copying this. They're just always prepared for chain rule. And if they're lucky enough to get a plain log x, well, they can apply this. That is 1 over x. The du, the derivative of a plain x, would be a times 1 at the end. So that this comes up so often that people just use this and they could apply it for the rare times that they get something this perfect. Okay, so back to here. So our function, not product rule, not product rule, 2 pieces, both need chain rule separated by subtraction. And as I look a little deeper into those pieces, there's no natural expansion. These are both as simplified, as expanded as they're going to get. So I'm again jumping into the derivative. 2 pushes along. log of this, the derivative becomes 1 over this times the derivative of what's inside. I'm going to make a little mistake here, everybody. My du part, the derivative of u, would be 5x to the 4th minus 6. I know I haven't finished. That's not what I'm talking about. But do you see my little mistake right here? 1 over u du looks pretty good, but realize du, all of du, always has to be multiplied by everything that came in front. So this needs parentheses. Without the parentheses, it's just the 5x to the 4th that's being multiplied, and the minus 6 is just floating along. But now all of that is du, all of that times this. The second part, the minus 12 pushes along. Log of cosine, the derivative starts 1 over cosine, and then times the derivative of cosine, negative sine. The second little thing, I pointed out up here a couple of little mistakes that people make when they're first getting used to natural log and its derivative. But here's the second thing. Now that you're seeing some of these slightly harder problems, the u here goes to the denominator, but the du portion, this is attached by multiplication, and the du portion can always be treated like it's over 1. That portion is in the numerator. So don't accidentally make that second little mistake people make where the u is in the denominator, so the du slides into the denominator as well. That's not how it works. 1 over u times du. Some people, honestly, they just would rather write it du over u. You're always getting 1 over, you're always multiplying by du. So some people just putting that a little bit together, just put the du right on the top. This goes right here. This goes right here. I mean, that would be my second step as far as cleanup is concerned anyway. But in this problem, there's also a tiny bit more. Oops, I'm sorry. Here we are. So now, just as I do my little bit of cleanup, yeah, this can go on top. But while I'm at it, why don't I distribute the 2 there as well? So instead of having all these parentheses, put all this together, 10 x to the 4th minus 6 over x to the 5th minus 6x plus 1. Over here, well, minus 12 and that minus sign will become a plus 12. And if I put this together, certainly sine over cosine is perfectly correct. But that's where, hey, we recognize that's its own trig function. Sine over cosine is tangent. So there. And look at what happened here. I don't think the derivative was that tough, but just looking at the cleanup, this still looks pretty messy, and that looks a lot better. Oops, I'm sorry, I just noticed that should be minus 12 here, right? 2 times the whole thing, 10x to the 4th minus 12. Okay, let's keep going. We're still finding the derivative. But now problem 3, let's look at x to the 5th times tangent cubed, all divided by the square root of x to the 4th minus 1. I could have started with a slightly easier example, but this is my next big point when taking the derivative. Mentioned in the previous video, now we're seeing why that is the case. But anytime we go to take a derivative of a log function, it is always in our best interest to simplify, and what I mean by simplify, expand as much as we can. If you just jump right in and take the derivative just the way it stands, well, it's not that bad. You start off with 1 over this. So 1 over this whole gigantic thing, well, 1 over a fraction flips your fraction. It's not that bad. But then I need the derivative of this. Do you see how terrible that would be? To take the derivative of this the way it currently stands, you would have quotient rule as the big picture, but when you go to take the derivative of the top, you would need product rule, and inside of that product rule, this would be chain rule, and when you go to take the derivative of the bottom of the denominator, this would also be chain rule. This would mix product, quotient, and chain rule, and has a trig function all mixed in all at once. Wow, that would be ugly. So can you do it? You can. There's lots of bookkeeping involved, but you can do it. So let's not take that approach. Let's realize, as I said, the best way before we jump in with log functions is to fully expand them. So this is still the original function. I'm doing a little rewrite. I'm doing a little manipulating before I jump in and take a derivative. So I'm going to expand this. And this is where, again, take your time, log of the top minus log of the bottom, and then the top can break up more. I'm going to leave this for you to figure it out. I'm going to jump to the final fully expanded version. And I would have 5 log x plus 3 log tan x minus 1/2 log of x to the 4th minus 1. I'll go, and now I'm not going to write it out, but at least to point out, multiplication separated by a plus, now the 5 can come out in front, and now the 3 can come out in front. Division, that goes from the bottom, gets a minus out in front, and the square root was the same as the 1/2 power. So that was definitely fast, but that will now make my derivative very simple. Now there's 3 pieces, and these are not the easiest, but we're kind of like in a combination between like this is very basic and these slightly harder. But if we have some good practice here, any of these types of pieces are very simple. And that's exactly what we have here. So C prime 5 times 1 over x plus 3 times 1 over tangent times secant squared minus 1/2 1 over x to the 4th minus 1 times 4x cubed. Coefficient pushed along, derivative log 1 over x. Coefficient pushed along, derivative log 1 over this times its own derivative. Minus 1/2 pushed along, derivative of log 1 over this, the derivative of the inside. See what I mean? Took our time to expand, had a much, much easier time. Technically, these two are still chain rule, but like we keep suggesting, chain rule is so common with logs so that it's not as bad as a lot of people first feel. When you first learn chain rule in Calc 1, it could definitely be frustrating, but hopefully you're getting good practice so that you're feeling better using the U's on my chart to get these derivatives. And that's really the situation. If we needed more than these basics and that little bit of chain rule, that just points out we could have expanded more. But now we've had a good derivative, and this is a good answer, but I'm just going to finish with just, again, a little bit of cleanup. That becomes 5 over x. Here, I'm just going to write this as 3 secant squared over tangent. Here, I'll take advantage. The 4 and the 1/2 can simplify, so I'd have minus 2x cubed over x to the 4th minus 1. Some people might play some more games here. Tangent is sine over cosine. So 1 over tangent is cotangent. I mean, that's one little trick right here, that's a cotangent. I mean, again, little things like that, that's your choice. Okay, the trig functions, you do have that ability to just make some slight manipulations. And at the very end, that if you want to treat this again, so this is 1 over sine over cosine, so cosine over sine, but then this is 1 over cosine squared. You could simplify a little bit. You'd end up with 1 over cosine sine squared. So again, you could keep playing with this, manipulate a little more. You shouldn't let the trig functions bother you that much, but you should be able to manipulate them to some degree. Okay, number 4. Let's get a little more practice with this. Let's take a look at log of, let's do e to the x squared divided by cosine x. Not as bad as number 3. Still a little messy though. So once again, not as bad. If you try to take the derivative right now, 1 over this, not bad. Then you got to take the derivative of this. At least it's only quotient rule. Technically, there's a little bit of chain rule right here. But again, just like the log u and e to the u, eventually people almost stop seeing it as chain rule and just realize that's how you treat all of the e to the u's and log u's. So not terrible to take the derivative right off the bat. And to realize one tiny little option as well, cosine in the denominator could be treated as a secant in the numerator. So just little things, still just basic manipulations, but either way, whether you prefer this way versus this way, either way, I'm still going to simplify. So this one, by having division, I'll simplify that. I'll expand that, I should say, into this. Here, you'd have log of secant plus log of e to the x squared. So again, very, very similar. And that helps us a lot. But realize here, some people that's good enough and they'll take a derivative and it's not terrible, but you could still clean this up. And not just clean this up, like this cancels. The log and the e cancel, and all you've got left is the x squared. Oops, that is not d prime. That's original d. That's just manipulating the original function. And now there's not even a log left right here. So the derivative, that would just give me a very simple 2x minus 1 over cosine times negative sine. We've seen that already. And that would be a plus tangent. But like I said, little things. If somebody does it this way, thinks of it as secant, now their answer looks slightly different, but manipulation, you can get there. People who forget to clean this up any further, they end up with x squared log of e, and they start doing product rule. That's a number right here. So you don't need product rule. That's like having 4x squared. You're really just working on the x squared. But then even here to notice log of e to what power gives you e? This is 1. But if you left it exactly the way it was and took the derivative, you get a 1 over e to the x squared. But then the derivative of e to the x squared is itself, and then we get an extra du. It's so easy to miss that here because you feel like you've already repeated the e to the x squared, but at this stage you didn't take the derivative of that part yet. At this stage you are just taking the derivative of log. And this is where you took the derivative of the e, so this is where it repeated, and that's the du. So there's your 1 over u, and all of this is the du if this is your original u. Okay, so let's get a couple of problems. Let's use the derivatives as well as getting a little more practice. Let's do a tangent line problem. Let's find the equation of the line tangent to the function f of x. We'll have e to the x cubed minus 1 plus 7 log of 4x, sorry, not plus 7, plus 2 log of 4x minus 3. And that's enough. We don't need more pieces. That's enough here. And let's find the equation of that tangent line at x equals 1. Okay? Actually, you know, let's just add one little piece. Let's put a minus 5 at the end. So, equation of the tangent line. I need an xy pair, and I need a slope. I gave you an x. I'm going to start by finding the y, and I'll plug that back into the original function. When I plug that in, I get e. 1 cubed minus 1 is 0, so I get e to the 0, which is 1. Plus 2, when I plug the 1 in here, I get log of 4 minus 3, so I get log of 1. E to what power gives you 1? That answer is 0, and 2 times 0 is 0. And the minus 5 still just hanging on. So we get a final answer of minus 4. Second part, the slope. Well, I need f prime of 1. But I'll start by finding f prime of x. I'll get e to the u, repeats itself, times du. And I'll just move that 3x squared to the front. Plus 2 times 1 over 4x minus 3. The derivative of the log is 1 over, times an extra 4. And the derivative of minus 5 would just be a 0. I've kind of already done a little cleanup here, but I'll take advantage. I didn't do it here, so I'll write all this again nice and neat. So if you didn't move that to the front, now is a good time. Now you don't need any parentheses. Similar over here, I'll make that a plus 8 over 4x minus 3. So that is f prime of x. So f prime of 1, plugging in 1, 3 times 1 squared is 1, times e to the 0 is 1, so 3 times 1 is 3, plus 8 over 4 times 1 minus 3 will give me 8 over 1 is 8. So the slope is 11. Make sure you finish the problem, everybody. Such a common mistake. I know you're in Calc 2, you've done a lot of hard work. Make sure you answer the question. You've got all the information, but now let's put it together. And unlike the one we did with exponentials, you're not lucky enough that this is just b. So as I always say, I encourage you to use the y minus y1. When I plugged minus a minus 4, I just made that a plus, equals m x minus x1. Good answer. Again, though, I have no problem on any test if you leave an answer like that, but if you want to check the answer in the back, they will solve it for y. So you'd have 11x minus 11, and you'd subtract the 4 over. So that would be an alternative answer. Equally good. Both of them are just fine. Okay, so you're seeing tangent line problems. That's a couple of times now. This one mixed both e's and logs together, but at least the derivatives weren't so bad. We've had, you could have product rule, quote, anything can happen here, but the overall step process, having the x, using that in the original function to get the y, and then using that x in the derivative. First, getting the correct derivative, and this is where simplifying matters more. So much easier to plug in when you've got a simplified, cleaned up version versus a messy version. Okay, second problem. Let's find the critical values for g of x is log. Let's do x squared minus 8x minus 9. Critical values where the derivative is 0 or undefined. Well, I better start off by getting my derivative. So it's just a simple function. Nothing fancy here, nothing to break up. So log of u, 1 over u, times du, and the derivative here would be 2x minus 8. So I'm just going to throw that right in my numerator. Again, critical values where the derivative is 0 or doesn't exist. When you get a fraction like this, when does a fraction equal 0? You could set the whole thing equal to 0 by cross multiplying. You'll end up only needing to solve where the numerator equals 0. Now that only works if you have one fraction. If you have two fractions, well, you got to combine them to make one fraction, get a common denominator, but only one fraction. So how is a fraction 0? Well, 0 over 10, 0 over 2, 0 over negative 3. As long as the top is 0, the whole fraction equals 0. So you only have to solve, and that'll give me my first critical value of 4. But also, we have to remember critical values where the derivative doesn't exist. That is where the denominator equals 0. So g prime does not exist. We're going to have to set the denominator equal to 0. And now just a coincidence. Here that was a little straightforward. Add the 8, divide by 2. Here a little bit tougher. You're going to have to factor. But not that bad. And all of these, here we are. All of these are your critical values. Okay, last thing to cover in this part. Lots of derivatives. Still have, lots to practice, getting used to the basics of ln, ln the derivative 1 over u du. Couple of good reminders. Again, these problems, they can come up with any functions. big picture, knowing how to find the tangent line, knowing how to find the critical values, and then being able to apply it to any situation. But the last thing before we move into the antiderivatives, start using this in the other direction, the other thing we have to discuss is this idea that is called logarithmic differentiation. And let me start off by showing you a little bit of a problem. So let's start off. This technique is for finding derivatives. So my directions are simply find the derivative. And let's start off with the function, what was I up to? I guess I used f and g on the previous page. So let's call this one h. Let's find the derivative of x to the fourth e to the 2x cubed minus 5 divided by 3x minus 1 to the third power times the cube root of sine x. And this is again a nightmare. Just taking this derivative, quotient rule, but then both the derivative of the top and the bottom. When you get to those sections in quotient rule, you would need product rule, and then you would also need product rule down here. Technically, there's a little bit of chain rule on this part. Both of these would contain chain rule. So just again, lots to look at. And you know what? I'm sorry. Let's make this 3x minus 1 to the 10th power. Just I have a lot of 3's running around. I don't like coincidences. So let's just make that to the 10th power. So again, could you take this derivative using your traditional means? Yes, you could. It would be tough. It would be a lot of bookkeeping, keeping track. What are we up to? What's still left to come? But now let's realize how the expansion properties of logs can help us here. If it was log of this whole function, well, now all of a sudden we'd be looking at this in a completely different light. And we would be saying, oh, well, now you've got the log of this whole mess, so now I get to expand it, and then we're back to an easier situation taking the derivative. That is what we are going to do. But the issue is, I can't just bring in this ln from nowhere. Just like every other equation, what I do to one side, I have to do to the other. And now what has changed is that now this is no longer a straightforward derivative. Technically, this left side is like having log of y. And we saw this at that very, very first proof. I did that. And I point out, if I want to take the derivative with respect to x here, I need to now start using implicit derivatives. And that's what's happening here. I want the derivative. I want h prime of x, which in alternative notation is the same as dy dx. So if you treat h like y, you want dy dx. So to do that, I'm going to need to take the derivative with respect to x. I apologize, I should have left a tiny bit more room, but I'm using the d over dx notation of this whole thing. The right side, well, before I take that derivative, I'm still going to expand this, simplify as much as I can to make this side as easy as possible, but I want to jump to this side because what happens here will happen every time we apply this technique. It's called logarithmic differentiation because you're bringing a log that wasn't there in before you take the derivative. And on this side, this will always happen. You take this derivative, you will get 1 over y times dy dx. Over here, you just take your derivative and get whatever you get. But at the very end, you have to solve for dy over dx. And again, this happens every time. You bring a log in, this will always be the left side. How do you solve for dy dx? You'll have to multiply this y to the other side. So for some people, instead of doing the implicit derivative every time, they just remember this, that when you bring the log in, that allows you to expand, but then your last step at the end, whatever answer you thought you had, always multiply by that original equation. So let's do it. So before I take the derivative, I have log of h. If you want to change it to y, that's fine, that's your choice. But on this side, I'm expanding. I'm not taking the derivative yet. I'm still going to leave that out in front because I still want to fully expand. Just like we always say, right? We want everything ready before we take our derivative. So let me do all that expanding. I'll get a 4 log x. I started log x to the 4th, the 4 out in front, plus log of e to this power. The log and the e would cancel. So I'd be left with 2x cubed minus 5, minus, because this is in the denominator, and that 10 is on everything. So I get minus the log of 3x minus 1 to the 10th, and the 10 goes out in front, minus the cube root becomes a 1/3 log of sine x. And now I'll take the derivative of everything. So on this side, I could use this notation. I could do it in my regular function notation, 1 over h times h prime. But now I'm using regular derivatives. 4 times 1 over x, I'll already clean up 4 over x. Again, here we were lucky the log and the e cancel. There's not even a log here. So this derivative, I get a 6x squared minus 0. Here, minus 10, 1 over 3x minus 1 times an extra 3. That 10 and 3 can go in the numerator as a 30. Last, minus 1/3, 1 over sine times the derivative of sine, which is cosine. Cosine over sine, that's fine. I'm going to write it as cotangent. And it feels like you've got a good answer, but again, when you have this extra piece, when you don't have exactly y equals or f equals, well, then you got to make sure you solve for the derivative at the end. So solving for h prime, I got to multiply both sides by the original h. But here's the last catch, everybody. I know it's a little messy, but don't be lazy. Don't leave that. So h prime equals all of this times this was the original h. So that's the good habit, everybody. Just make sure you get back. And don't just write times h or times f or times y. Make sure you get back what was that original h function or that original y function. X to the 4th, e to the 2x cubed minus 5 over 3x minus 1 to the 10th, the cube root of sine x. Let's do that again, everybody. So good practice, but let's see that again. Find the derivative, keeping those same directions, but now number 2, let's look at function j of x, and we'll let j of x be x cubed plus 10x minus 1 to the 5th power times secant to the 4th power times, let's do the square root of 12x minus 5. Lots of multiplication here. If you are going to take a derivative in a straightforward way, you'd have to use triple product rule, and every one of these individual pieces would need chain rule. So probably a little bit easier than the one we had up here, but only by a tiny bit. So one more time, very tough situation. Lots of product and chain. No quotient rule this time, but lots of product and chain rule. So I'm going to take the log of both sides. This side, well, that's as good as it gets. That's log of j. But on the right side, now by having that log, now I can expand this log of this plus log of this plus log of this. And now that exponent can kick out in front. Plus the log of secant to the fourth will become 4 log of secant. Plus the log of the square root. Well, the square root is the 1/2 power. Log of 12x minus 5. Now I'm ready for a nice, fairly simple derivative. So now I'll take my derivative. And this is what I'm saying. Some people, they just concentrate over here. They know there's that little bit at the end, so they make sure they put that bit at the end. But now they just kind of remember there's that extra step because it'll always work out the same way. But I'll show it to you again. Now I'm taking the derivative on both sides. Maybe you want to put that notation for yourself. Maybe you just literally want to write taking derivative. But now is when I'm actually doing that. So 1 over j times j prime. Here, 5, 1 over x cubed plus 10x minus 1 times 3x squared plus 10 plus 4, 1 over secant x times secant x tan x. I'm being a little more thorough this time. I've been doing a little bit more in my head on the previous, so to do another one out very thoroughly, I just need a little room, so I'm going to take this derivative and sneak it right here. Plus 1/2, 1 over 12x minus 5 times an extra 12. I'm not worried if you don't simplify, clean up this part, but make sure for your final answer, it's not just this, it's all of this times the original j. So now I will take advantage and do a little cleanup. I'll distribute the 5 through here, 15x squared plus 50 all over x cubed plus 10x minus 1. Here, I'll take advantage of the secants canceling, so that'll just end up being 4 tangent. And then over here, the 1/2 and the 12 would give me a 6 over 12x minus 5. But the big deal is not that cleaning up. The big deal is all this is, again, times that original function. And that is your final answer.